Hi again, everybody. Welcome back. This is an extension of example 9.4 that we did in the last video segment, and that was on the two canoes experiencing a force. And we found the final momentum of each canoe was the same, even though they had different masses. So let's just look at this real quick. I'm going to draw two canoes. There's canoe 1 with 2 people in it, and canoe 2 looks like bananas, doesn't it? 2, 3. With 4 people in it, and obviously the masses are going to be different. Okay. Well, this momentum initial of 1 equals 0, and momentum initial of 2 equals 0, and so we can say the momentum of the system equals 0. Well, after they pushed off, there was a 46 Newton force between them, and they pushed off for a few seconds. Okay. So this canoe is shooting away this direction, and this canoe over here is moving away in this direction. Maybe not as fast, right? Because there's more people in it, there's more mass. All right, we said that the final momentum final here, is negative 55.2 kilogram meters per second, and this momentum final equals 55.2 kilogram meters per second. What is the momentum of the system here? Momentum of the system is still 0, because these add up to the same thing as the initial momentum add up to, and that is 0. All right, so in this way we can say that yes, momentum was conserved. The same amount of momentum beforehand, we'll say initial and final, is going to be equal. Even though the two parts of the system are moving away in different directions, the combined momentum of the whole system is definitely going to be equal and going to be therefore conserved. Of course, now let's ask ourselves, was energy conserved? And I'm going to draw this in blue. All right, was energy conserved? So really, the question is the same amount of energy in the system beforehand and afterwards. Okay. Well, beforehand, what's the energy right here? Energy of 1, and energy of 2 right there. Well, they're not moving at all. Right? And they're not elevated at any height off the water, so there's no potential energy. So you could say that the potential energy, the kinetic energy, in both cases is 0. All right, energy equal kinetic equals 0 because it's not moving. Kinetic equals 0. Okay, but finally there is, that is after the push, there is energy. Energy final 1 and energy final 2. What's energy final 1 going to be? Well, it's going to be kinetic, right? Because it's moving. It's a mass that's moving. 1/2 mv final squared, and 1/2 mv final 2 squared. It's v final of 1 squared, right there. Okay. Now, we don't know what the V finals are. We do know the masses, but we agree that these have some velocity. This is some velocity in this direction, probably less than the canoe with less people, because with less people you're going to be shooting off much faster. But there is going to be a K final for 1, and there's going to be a K final for canoe 2. All right, but the difference here is that there's no arrow over the K here, as there is with momentum. That is, energy is not a vector quantity, it's a scalar quantity. Momentum, you can have negative 55 kilogram meters per second and 55 kilogram meters per second and have them balance out to 0. But energy is energy in any direction. It is without regard for direction. And so this is going to be some final kinetic energy and some final kinetic energy right here, and these are going to be added together, and that's going to be the energy of the system. should say E cis right there. Got kind of a little messed up. E cis. Well, here the energy of the system equals 0 plus 0. Here we have the kinetic energy of the one canoe and the kinetic energy of the other canoe. So where did that come from? Where did this final energy of the system, which is much greater than the initial energy of the system, come from? Well, it came from the guy pushing. Right? The guy, he pushed, he applied a force over some distance and over some time. That's work right there. So the guy from the one canoe pushing did work on the other canoe to give both canoes a little bit of energy, a little bit of kinetic energy. But energy was not conserved because he put work into the system. So that's why the final total energy is greater than the initial energy. So no, energy was not conserved. No right there, but momentum definitely was conserved. Yes. All right. So for this last part right here, where it says write a general rule for how forces, internal and external, affect the momentum and total energy of a system of objects, what I'm going to do for that is take all this stuff and just shrink it down a little bit like that and give us a little more space. And I'm going to write it in the form of kind of like a matrix. All right, and I'll show you what I mean here in just a second. I've got 2 by 2 matrix. All right, so external forces and internal forces, and do they affect the momentum of the system or the energy, the total energy of the system? Yes or no? Okay. So let's look at internal forces first, because we've been talking about that. All right. Do internal forces, did this internal force right here, the push from the one guy, that force right there, did that affect the momentum of the whole system? No, it didn't, because the momentum here was negative and the momentum here was positive, and so they added up to 0. So does it affect? No. I should do that in red because it was in red. No, it does not. All right, just put a big N right there. But do internal forces affect the energy of the system? And the answer is yes. If there's an internal force created by a person in the system right here, the person's doing work, all right, they're pushing the two canoes apart, and they went from having no system energy to having this total kinetic system energy right here. So for that, the answer is yes. You can have internal forces, should be a Y right there, right? You can have internal forces affecting the total system energy. Again, because energy is a scalar, not a vector quantity. Well, let's look at external forces now. And let me get a different color right here. We'll do purple, all right? An external force, as we mentioned before, is a force that comes from somewhere outside the system, not from inside. So let's just say these two canoes were sitting right here, and there's a big force, we'll say a wind gust, all right? An external force, a wind gust, coming and being applied to both of those canoes. What are they going to do? First of all, they're going to go from 0 momentum, because that's before the wind gust, to all of a sudden they're both going to have momentum in the positive direction. So is both of them having a momentum in the positive direction, is that going to cancel out to 0, like the original momentum of the system? No, definitely not. Right? They're both going to have some sort of positive momentum. It's very different from 0 right there. So will external forces affect the momentum of the system? Absolutely. Absolutely. Do they affect the energy of the system? Well, right here, what's the energy of canoe 1? 0. 0 kinetic energy. Canoe 2, 0 kinetic energy. If this external force, we'll say the wind, blows on these and they both move off to the right with some velocity, do they have energy now? Both of them, yes. Do the energies cancel? No, because neither of them has a negative energy. They both have positive energy. Energy is regardless of direction. So external forces can also affect the energy of the system. The only thing that does not affect the system is internal forces. They do not affect the momentum of the system. But everything else is affected by a force. Internal forces affect energy. External forces affect momentum and energy of the system. All right, so that's kind of our general rule right there for what types of forces affect what kind of properties of the system. All right, I think that'll do it for this segment. Thanks for following along. I'll see you on the next one.